To calculus 1. This part it is mostly for reviewing purpose and the background necessary to get calculus 1 started. Okay, so mostly the material it is from chapter 1, but anyway I don't necessarily follow sections by sections or page by page. I just list out, first I list out some important formulas we use a lot in calculus. And so these are the formulas I have. The first part, so-called multiplication formulas. This is the first formula. I suppose you know this very well. Really comes from FOIL rule, right? I suppose you know the FOIL rule. F is for the first term, O is for the out term, and then I is for the inner term, L it is for the last term. The FOIL rule, mostly I'm saying this part, the first two formula, it is about the FOIL rule. I call this as the square of a sum, which can be expanded into those three terms. Okay, and also the second formula, that is the square of a difference, also can be expanded into three terms. And really, I want you to know, I hope you already know that these two formulas, they are equivalent. They are equivalent, right? And also for the third and the fourth formula, they are equivalent too. And the third formula, it's the cube of a sum, which can be expanded into those four terms. And the last one, it is the cube of difference. Still, there are four terms. And then indeed, we really do need to use formulas a lot, and you do need to know them very well, very well. Multiplication or expansion formulas. And also we do have some factorization formulas, common factorization formulas. I call this as the difference of two squares, which can be factored as the product of sum and the difference. And also this product, sometimes we call this as the product of conjugate pair. This is a product of conjugate pair, turns out to be the difference of squares. And also the next one, it is difference of cubes, which can be factored as product of these two. And also the third formula of factorization, it is sum of two cubes, which can be factored as a plus b times a squared minus ab plus b squared. And also, if you look at all the formulas together, we do have the square of sum, square of difference, and then we have difference of squares, difference of cubes, and then we have difference of a sum of cubes. And then you may wonder if there's a factorization formula for the sum of two squares. As a simple answer, I want to say no. And also just want to make sure we are doing calculus mostly for our purpose. We are just going to consider real numbers. And if you have the knowledge of complex numbers, and then we do have the formula of the sum of two squares by using complex numbers. But anyway, for calculus purpose, mostly we consider real numbers. So I do not include the sum of squares formula here. These are the basic formula, very basic formulas. You got to know them very well. And also, I do not list out any specific examples. I would say for these formulas, you really don't even want to bother with the textbook. Try to provide one or two simple examples for each formula. Then take a look again if they really make sense to you. You need to know all those formulas very well. The multiplication formulas, mostly they are just based on the FOIL rule, and certainly relating to the power 3, it is really the product of 3 of those same things. It's just, you really need to multiply them out one by one, term by term, okay? Then by arranged terms, and you get the formula. Factorization formulas, some of them they really come from those multiplication formulas. It's the reversed FOIL rule, okay. And so we do have the different squares and the different cubes, and also we have sum of cubes and no sum of squares, no factorization formula for sum of squares. And also the other thing that I want to review here, it is about the exponentials and the logarithms. So first, take a quick look about an exponential term. This is the exponential term I'm talking about, b to the power of n. Let's say n is an integer, okay, like a b to the power of 2, b squared, b cubed. B to the power of 2, certainly no doubt, that is b times b. B to the power of 3, that's a product of 3 b's. Then b to the power of 10, it is a product of 10 b's. And also, don't forget there is a special case. What will happen? We do consider in mathematics raising to the power of 0. B to the power of 0, simply it is 1. It is 1. And also the thing about exponentials might be more complicated is not only we have those positive integer powers, we may have negative integer powers. So if that is the case, we can move this, change the exponent to positive, then move the entire exponential term to the denominator. For example, b to the negative 2 is 1 over b squared. B to the negative 3, it is 1 over b cubed, and so forth. Well, exponentials are complicated. Not only we have positive integer powers, we also have negative integer powers, and also we may have a fractional power, like a b to the power 1/2. I hope you understand the b to the power 1/2. That's a square root. Okay. That is the square root of b. And similarly, when we have b to the 1/3, that is the third root of b. And simply put, the denominator of the power, it is the radical index. This n, it is the radical index. The denominator of an exponential, the power of the exponential term, it is the radical index. This n, it is the power, the denominator of the power, right? Sorry, I cannot highlight this. This n, it is the denominator of the power of this entire exponential term, which converts to the radical index right here. And also, we could have a rational power more complicated, b raised to the power of m over n. And it's the denominator, so that is the radical index. The numerator of the power, it is the actual power. But anyway, when you convert it into radicals, there are two ways to handle this power. And you could handle this numerator m as inside the radical notation. And also, you could put this m outside the entire radical notation. They are the same. And well, it's easy for me to say. I'm not sure if you really get the idea what I'm talking about. I would say try to provide some simple examples to see if you are convinced. I'm saying maybe you want to give a try if you can handle the situation like 8 to the power of 2/3. Then try to see if you can figure out the meaning. I'm saying, for example, you could consider 8 to the power of 2/3. Try to see if you can simplify the answer. Or you could give a try 25 to the power of 3/2 and still try to see if you get a simplified answer. I mean, without using a calculator. And then if you are convinced by the actual rules, okay. And also, we do have some other additional properties of exponentials, and these are called the laws of exponents. When you multiply two exponential terms together, we can keep the product into a single exponential term with the same base, and then add two exponents together. When you divide the two exponential terms together, divide the two exponentials with the same base, and you keep the base, you subtract exponents. Okay, and this is the only time, the line here, this is the only time you want to multiply two exponents together. In words, I say this is in the fashion of raising power, a power term to another power, raising power to a power. This is the time you want to multiply two exponents together. Otherwise, I would say mostly you don't want to multiply those powers. Okay, only in the case raising power to a power, you multiply two exponents together. Laws of exponents, definition, how an exponential term is defined. And before I end this part of discussion, I want to talk very quickly. Just want to present one formula. It's about logarithms. Believe it or not, whenever we have exponentials, most cases we also need logarithms. So I don't want to explain a whole lot. It might be hard to understand the logarithms. Put it in a simple way, mathematically, I want to say a logarithm, it is an inverse of a corresponding exponential term. So I do have a single line here in the end. B to the power of y equals x. Y, it is the exponent. And sometimes we do need to focus on this exponent, not the exponential of the entire thing, the power, the exponential term, the entire thing, only the exponential part. Okay, so if that is the case, we can write this exponential term in an alternative form or in an equivalent form. Focus on the exponent, so the exponent is, okay, it is a logarithm. The base of exponential term, it is the base of the logarithm too. Y, it is log base b of x. I'm saying two things. The logarithm, it is used to represent an exponent, and a logarithm, it is an inverse of an exponential term. So let's take a break. We will continue to review in our next part. Thank you for watching.